This is Module 5, Lecture 2, Regression when x is binary. Okay, sometimes we have a binary regressor, just like we had a Bernoulli random variable at the beginning of the course. We're talking about a variable that takes on only two values, x equals 1, for example, if we have a small class, x equals 0 if not, or x equals 1 if we have a female, x equals 0 if male, or vice versa. X equals 1 if treated, or x equals 0 if control, not treated. These are sometimes called dummy variables. Don't ask me why. This is just convention. So far we've called beta 1 the slope, but what if x is a dummy variable? The slope doesn't make sense. And so I've drawn this little graph up here. X equals, it only takes on the two values 0 and 1, and y is just going to be some data points plotted like that. So there really isn't a line to be drawn here. There's no beta 1 that we can call a slope. Interpretation of binary regressors. So suppose we have the model y I equals beta 0 plus beta 1 xi plus ui, where x is a binary variable, xi equals 0 or 1. When xi equals 0, yi, so this portion right here drops out, right? So if x equals 0, then that part drops out, and we're just left with yi equals beta 0 plus ui. So yi equals the intercept. The interpretation is the mean of yi when xi equals 0 is beta 0, or the expected value of yi conditional on xi, or in other words, the mean of yi conditional on xi equals 0 is equal to the intercept, beta 0. One thing to note here is that we're tying a regression to an expected value. We haven't really talked about this, but this is why we did expected values at the beginning of the course. Regression is really just estimating a conditional mean. Conditional mean being the expected value of some random variable y, conditional, remember this line means conditional on x taking on certain values. So that's why we did the expected values at the beginning of the class. The regressions are really just estimating mean values of y conditional on your x variables. If x was a dummy for male equals 1 and female equals 0, this would be the mean of y for females only. So when we're saying x equals 0, so we're talking about females, would be the mean of y, whatever outcome it is for females only. When xi equals 1, yi equals beta 0 plus beta 1. So notice how xi still drops out, but we're now multiplying beta 1 by 1, talking about right here. And so we're just left with yi equals beta 0 plus beta 1 plus ui. The interpretation is that now we're talking about the mean of yi when xi equals 1, which is beta 0 plus beta 1. In other words, the expected value of yi conditional on xi equals, this should be 1, equals beta 0 plus beta 1. So the difference, the previous two statements imply that the difference between these two, expected value of yi when xi equals 1 minus the expected value of yi when xi equals 0 is beta 1, or our quote-unquote slope parameter. But what it really is the difference in group means, or the difference in the average y for males and females if x is a dummy for male versus female. So let's do an example. Let's say di is equal to 1 if the student-teacher ratios are less than or equal to 20, or we'll call this small classes. Whoops, classes. Well, in 0, if we're talking about large classes, the student-teacher ratios are greater than 20. The OLS regression output, if we estimate the relationship between test scores and this dummy variable, is given in the equation here. Beta hat 0 is 650, and beta hat 1 is 7.4. Remember, these are your standard error estimates for those variables. Okay, so we can do this by hand. This is a little bit, this is not really complicated. We can actually go back here. What is this saying? So if di is equal to 0, we're talking about large classes, right? If we set di to 0, then we're just left with beta hat 0 which is equal to 650. So that says the average test score for large classes is 650. If DI is equal to 1 for small classes, that says that we're taking beta hat 0 plus beta hat 1, which is equal to 650 plus 7.4, meaning that the average test score for small classes, we have to add on this extra bit, beta hat 1, to get the average test score for small classes, which would be 657.4. And what beta hat 1 is really telling us is the difference in test scores for large and small classes. Let's do this by hand. Okay, so we have class sizes small and large. Average scores y bar for the small classes are 657.4. Average scores for the large classes are 650, with standard deviations over here for each of those, and number of observations here. The difference in means is y bar small minus y bar large, which is 657.4 minus 650, which is equal to 7.4, which should sound familiar because that's what the regression told us it was in the previous slide. This is the estimate we got of beta hat 1 from the previous slide. The standard error formula for a difference in means is given here. And when we plug all these values in, we get 1.8. And so we can actually go back and look at, we get the same values from our regression output, 7.4 and 1.8, that we do when we do this by hand. So the takeaways, we can take the difference in sample averages, y bar small minus y bar large, and we will get the same thing as if we had run the regression with our dummy variable. We should also notice that the standard error of the difference in means is the same as the standard error of the coefficient on D estimated with a regression package. Another example, suppose you want to find out if there's a difference in wages for males versus females, or is there a wage gender gap. So first we want to write down the population model where the dependent variable is wage and the independent dummy variable is male, which is equal to 0 for females and 1 for males. So we have male equals 0 for males, 0 for females, and 1 for males. So here's our population regression line. We want to specify our null hypothesis that there is no difference in wages for males and females. So the difference in wages for males and females is given by this coefficient here, the parameter beta 1. So our null hypothesis is that beta 1 is equal to 0 versus an alternative that beta 1 is not equal to 0. Now suppose you estimate the following regression. So I just wrote out several different ways to write your estimated regression line. You can write the actual data of wage for individual I is equal to beta hat 0 plus beta hat 1 times male I plus U hat I. Or you can write the regression line as the predicted wages, wage hats, equal to beta hat 0 plus beta hat 1 times male, but then you would have to leave off the error term here. And so our regression output gives us wage hat I is equal to 8.33 plus 1.03 times male with some standard errors. So let's interpret these coefficients. Beta hat 0 says that on average wages for women are 8.33. Why women, right? So if male is equal to 0, then this whole bit drops out, and we're just left with beta hat 0, and beta hat 0 is 8.33 dollars per hour. Beta hat 1, on the other hand, says that on average wages for men are, well actually this would be beta hat 0 plus beta hat 1, says that on average wages for men are 8.33 plus 1.03, or $9.36 per hour. This suggests that men make more, 1.03, $1.03 more per hour on average than women, but is it significant? Is this just random noise in our data, or is this a significant effect? How do we do this? Think back to Module 5, Lecture 1. Let's talk about the t-stat. So let's take our estimate of beta hat 1, subtract off the null hypothesis, divide by the standard error, and we get 2.45, which is greater than 1.96, so we reject at the 95% confidence level. So it is significant. Great, that's all I have for this one. See you in lecture 3.